let's get started. I apologize for the lack of music today. It's rough on me. So you guys may think that I play music before class because I'm trying to be cool or relatable or whatever, but that's actually mainly for me, to get me pumped up to teach. So I'm gonna try to achieve the same type of liftoff today just by sheer force of will. How was break? Thumbs up for break? People, hopefully some of you made it back safely. Obviously the people who are here are the ones who did make it back safely. People may be still stuck at the airport, but if you went somewhere warm, welcome back to somewhere that is not warm. And I'm really excited you guys are all back. So we have 2.5 weeks left in this semester. That's it. So you guys are gonna, you're gonna take 2 more quizzes. You're gonna take a midterm. You're going to do a final project. And that's it. Like we are almost done. We're gonna do homework problems for the next couple weeks, but the main focus at this point is doing your final project and preparing for the last midterm. So you guys have a quiz starting this week, and we will talk about some of the material from that quiz later today. So I have 2 goals today. The first goal is to finish up the discussion about the internet and web interfaces that we started on the Friday before break. And then at the end, I'm going to talk a little bit about sorting algorithms. That assumes that you guys let me talk. I know you guys haven't seen each other for a week. Wait and talk after class. All right, so last time we talked about the internet as this enormous piece of physical infrastructure, most of it wired. So most of the connections, most of the information that travels to the internet travels over wired connections. Most of those connections are fiber optic cable. So most of the path between you and Facebook.com or Instagram.com or whatever is on a tiny, tiny shard of glass that where information can travel, largely unimpeded over hundreds of miles, right? And so this is actually sort of one of the wonders of the modern world. If you think the internet is awesome, and I do, then you really have to, acknowledge the debt paid to glass, to our ability to make really, really clear glass and string fiber optic cable. None of this would be possible without that. There's also an increasing part of the internet infrastructure that's wireless infrastructure at the network edge. So again, the primary goal of the edge of the internet at this point is essentially to get your packets, to get your data to a wired connection. Typically, we are not using wireless connections for long-distance links. Your data doesn't get from here to Australia by bouncing off a satellite. It's way too slow. It does that by crossing underneath the ocean on fiber optic cable. But, we have this edge of the internet where wireless connections are frequently allowing us to be always online in an untethered way, right? So the Wi-Fi that we have blanketing this room, you can see all the access points around here. I think there's at least 8 in this room. And then, so short-range wireless, which is typically dominated by Wi-Fi, and then medium-range wireless as well. So somewhere close to here, if you have a phone out and you're connected to some wireless tower, there's some piece of cellular wireless infrastructure that you're connected to as well. So these 2 technologies are largely responsible for providing that last hop or first hop connection to the internet that you guys are used to, right? It's very, a lot of you don't plug in a machine into the wall anymore very often, right? This is increasingly going to be true. You may have seen some commercials, if you guys, Verizon has some ads out now talking about how they're building 5G networks. So we're actually investing in even more infrastructure to provide faster connections at the network edge, wireless connections at the network edge, right? So this is something that you guys will see to continue to evolve through your lifetimes. And so essentially now, if you have a computing device, even a phone or even something smaller than that, you can maintain pretty much all the time, unless you're on an airplane, like the last place where it's sometimes difficult to get connected to the internet, you're always connected to 4 billion other machines, which is pretty incredible. So a lot of times, your first connection is wireless. After you get there, wired hops all the way there. All right. We talked a little bit last time about communication protocols. So now we have a communication medium. We have a way for me to send data, to send numbers, to send information from one machine to another. But that doesn't mean that I can use this medium effectively. I need to have things to talk about, so I need content, but I also need a way to structure the communications between multiple machines. And this is something that on the internet we refer to as a protocol. The protocol that defines the internet is something called the Internet Protocol, or IP. You may have heard of IP addresses, or IP routing. This is the protocol that gave the internet its name. This protocol does very little. It concerns itself with only a couple of important things that we need to agree on so that we can communicate. The first thing is, what do we call each other? So one of the big concerns of the IP protocol is addressing. When you connect a machine to the internet, it needs to acquire an address that allows it to uniquely identify itself on a system that 4 billion, 5 billion, 6 billion, 10 billion other machines are connected to. So this is the first concern of the IP protocol. And we showed a couple of different examples of IP addresses. The first form is ones that you might have seen or come into contact with. Those are IPv4 addresses. And then the second are a new variant of the IP protocol, IP version 6, that's allowing us to address one of the few weaknesses with IP. In many ways, IP is this beautiful protocol that has survived and evolved incredibly well, but its creators didn't anticipate that someday we would have 10, 15, 20 billion devices connected to the internet. There are only 4 billion IPv4 addresses. So to address this problem, we're slowly migrating to a new variant of the IP protocol called IP version 6. IP version 6 has longer addresses. Here's an example of one that allows us to address many, many, many more machines. So IPv6 is going to provide as many IP addresses as we could ever possibly imagine that we would ever need. The other thing that IP structures is the format of the message. So when you receive a message using the IP protocol, it's just a series of numbers, right? It's like you can imagine it in Java as just an array of a certain size that just has numbers in it. And you need to take that and somehow convert it to data, useful information. And so the IP protocol determines which part of this array, which indices of the array holds certain pieces of information. And so I can take this just big, long string of numbers that I got from the other computer that sent me information, and I can parse it. I can break it into smaller pieces that individually have meaning, right? One of the cool things about IP and one of the ways in which it has enabled innovation on the internet is it's a building block for lots of other protocols. And so we introduced some of these. HTTP, which we'll talk a little bit about more in a second, which is the protocol that powers the World Wide Web. So HTTP runs on top of the Internet Protocol. It uses the Internet Protocol to send data back and forth between machines, but HTTP introduces additional semantics on top of the Internet Protocol. SMTP. So these are protocols that you use every day, whether you know about it or not. Every time you go to a web page using HTTP, every time you send mail. The mail servers that transmit your message from you to your dad or you to your friend use something called the Simple Mail Transport Protocol to send mail from machine to machine on the internet. So this is another example of a protocol. DNS doesn't end with a P, but every time you go to, www.spotify.com, your computer is translating that human-readable address into one of those IP addresses that we just talked about. And that process uses its own protocol called the domain name service. And then again, we can actually invent new protocols and deploy them on the internet based on top of IP. So one of the things actually that's been happening that's really exciting in the web space recently is that we're actually starting to see new lower-level protocols being developed. And the company that's pushing a lot of that development is Google. So Google has successfully pushed for standardization of something called HTTP2, and now is actually pushing for the standardization of something called HTTP3. And without going into the details, what Google is starting to do is replace some of the lower-level protocols, not IP. These are all built on top of IP. But Google is able to do this. Why? Right? Why can Google do this? Because a lot of connections today are between one piece of Google software and a Google server, right? So if you use Chrome and you go to gmail.com, you're running code that Google wrote, Chrome, and you're connecting to a site that Google maintains, gmail.com. If you go to google.com, same thing. And so Google's been able to deploy some of these new protocols by essentially building them into Chrome and then building them into their own sites. And so they can, so even if it's only Google products that support these protocols initially, there's still a lot of connections today on the internet between one piece of software that Google owns and a server that Google owns. Depending on how you feel about Google, you may or may not like this. You may find it fantastic. I want to go work there. You may find it frightening. Google is sort of in control of a larger and larger amount of the internet ecosystem. But this is allowing them to experiment. And so they're trying out some new things that are built on top of IP. Everything's still built on top of IP. All right. So one of the things that's important to understand about the internet is it's not just the World Wide Web. That's a lot of your experience of it. But there's a lot of different information that's traveling over the internet, over IP, that's not web traffic. Mail, all sorts of other types of useful services that are built on top of IP that are not the World Wide Web. The World Wide Web is a specific protocol and set of, contents and other things. We're about to talk about that. Okay. So what is the web? So this is about where we left off last time. So the web essentially combines three different technologies. It's a protocol. So the World Wide Web allows a client to retrieve information from a website or web server using a specific protocol called HTTP, which we'll talk about briefly in a minute. It's a markup language, so the web also specifies some content formats. So these are ways in which the documents that you retrieve, the data that you retrieve using HTTP is structured. HTML, CSS, and JavaScript. So these three core technologies determine how the page is structured, how the page looks, and also what the page does. So we briefly talked about HTTP, GET, and POST. This is all we're going to do. We're not going to get into the details. The HTTP protocol specifies lots of different message types, but the most important to understand are GET and POST, particularly for the web interfaces that you guys are going to use as part of your, maybe going to use as part of your final project. It's one of the options. GET is how your web browser asks a website for a page. And we showed an example of this last time. I'm not going to repeat it. But GET is used to retrieve content. That's what it sounds like. I want to get something. I use a GET request. POST, on the other hand, is used to send data to the server. So GET says, I want a page. Please send me back this information. POST says, I have some data that I want to send to you, to the server. And so POST is used for things like submitting forms. When you pay for something, when you buy something on Amazon, you have to tell their server, here's the thing I want, here's my credit card information, here's where this is supposed to be shipped, et cetera, et cetera. There's all sorts of information you need to provide to Amazon.com in order to complete the purchase. So this is how you send data to another site. GET and POST have these different semantics. I'm not going to dwell on this. GET's not supposed to change the world. It just returns some information. So if I repeat the same GET request over and over again, nothing is supposed to change. A POST request, on the other hand, should change the world. How many people have seen that warning when it's like, do you want to submit this form again when you've been browsing the web? Yeah, we sort of started to make this go away, which is a good thing. But sometimes you'll see this. The reason is submitting the form twice can cause something to happen twice. Maybe you only want it to happen once. Maybe that thing is your credit card being charged for something, right? I don't want to buy the same item twice. Okay. So let's talk a little bit about what's actually moving around when we use the web. So GET is how I retrieve content from a server. What do I typically get back? What is the data that the server sends me? So there's three, the web is really four if you include images, but I'm going to show you three different pieces of web content. These are parts of the core technologies that power the World Wide Web. The first one is HTML. How many people have seen HTML, done anything with it? Okay, good, right? So this is, you don't see this, but this is right in front of you all the time, by the way. If you want to poke around and learn more about the internet, You already have the best tool in front of you. Many of you are using it right now to do that. That tool is called a web browser. Chrome will show you an incredible amount of information about what's going on when you browse a page. It will definitely show you the source of the page. So this is, you know, an example of a kind of web page that you might retrieve from a web server. HTML uses tags to provide semantic information about the page. So we're not going to go into this in detail, but here's an example. So an H1 tag, does anyone know what this is? What does this mean? Yeah. It's a first-level heading. So this is where it starts, this is where it ends, and what this page is telling my web browser is that this is a simple web page, is important in some way. It's a heading. It's important. Note that it doesn't tell me how it's supposed to look. I want you to notice this because this is interesting. Here's another example. So anyone want to guess what a P tag is? It's a paragraph. So what the HTML is telling me is that this text is a single paragraph. What about this down here? OL? LI? Any guesses? Yeah. Yeah, so an LI is a list item, OL is an ordered list. I also have an unordered list, or UL. So a list can be of things that are in order, and a list can also be of things that are not in order. Again, I want to point out, nothing about this tells me how things are supposed to look. This is semantic information. Okay? Strong, anyone want to guess? I mean, I'm sort of giving it away with the page. So again, this is, hello. This is a rough day on the internet here. There we go, okay. So, strong, this is important information. It's not important like a heading, but I want to draw attention to it somehow. Okay? Again, it doesn't tell me how to do that. It just says, you should do that with this text. So here's an example of how this is rendered. If I just load that page in my web browser, it's going to look something like this. So you'll see this text up here. How do I know it's a heading? It's bigger. That's part of how this web browser has chosen to indicate this to me. Down here, strong ended up being converted to having the text be bold. So I'm making a styling decision based on semantic information. Same thing with the paragraph tag. So the paragraph tag created a little bit of vertical space above and below that piece of text. Right? So when you guys see a web page, you see this. But what's being sent to your browser is always this. This is an interesting example of something that's known as markup. So this is just text. I'm not sending you an image. If I sent you an image of this page, it would be huge and very, very inefficient. So what I do is the web provides me with ways to provide semantics, provide styling information, which we'll look at next, and provide some programmatic content for the page, all in just text. So everything that your browser gets to render this page is text. If the page had an image, I would also send the image contents down, not as text, as an image file. But in this case, everything is just text. And the text includes these pieces of information about what the text means, or markup, semantics. Okay, so at the beginning, this is all the internet was this series of static sites, right? You would essentially, there's a file sitting there somewhere on a computer, and I ask the web server for it, and it sends it to me. The second thing that happened on the web is that the server started generating this file. So if you go to Amazon.com, for example, what happens? So when you send your request to Amazon.com, it knows things about you. It knows if you're logged in, it says, okay, who is this person? It looks at your purchasing history. It looks at, all the information it's been able to figure out about you based on what you've purchased and what you've browsed before. And it uses this to render the page. So the page that you see when you go to a website like Amazon.com would be different for everybody in this room. because it's being dynamically generated. There's no file sitting there on Amazon.com that's like jeffreychallen.html, right? That's all being generated on the fly. The last thing we'll look at is this example of web applications that have a completely different structure to them, right? We'll get there. Okay. So the second piece of core web technology is CSS, or cascading style sheets. Now this starts to tell me information about what the page should look like. Remember, HTML is not supposed to tell me how the page should look. It's supposed to tell me semantics about how the content is structured. CSS defines how the page looks. So here's some CSS, and maybe some of you have seen this before, maybe some of you haven't. But what does this say? So this says the body of the page, essentially the whole thing, should be rendered using a sans serif font. Sans serif font is one that doesn't have those little curly cues at the edge of the letters. Down here, what does this say? This says H1 headings should be rendered using a font that's of size 48 pixels, and it should be bold. So now I'm starting to see information about how the page should look, and that's exactly what CSS is for. CSS tells me, you know, again, this is a sans serif font. There's no serifs on it, and this is 48 pixels. So I've added this style sheet to the page that we looked at previously. So CSS tells me how the page looks. Okay, so here's by far the most interesting piece of the current web and current web technologies. This is code. So when you go to a web page, you typically get 3 different primary sources of information from the web server. You get a web page in HTML. You get style sheets, 1 or more, that tell you how the page is going to look. And the web server sends you a program to run. It sends you a piece of computer code written in a language today called JavaScript. JavaScript is a language that has nothing to do with Java, by the way. I know, I thought that for a long time. JavaScript and Java are totally different languages. They have no relationship to each other. JavaScript is actually older than Java. A lot of you probably wouldn't have guessed that either, by a couple of months. JavaScript tells the browser things about how the page should behave. It's code. It's a programming language with which you can write all of the same things that you wrote in CS 125 this semester, just different. You can write any program you want using JavaScript. Here is an example of a little bit of fairly ugly JavaScript. But what this is going to do, this sets a timer in the browser. The timer is going to fire every 1,000 milliseconds or every 1 second. And what it's going to do is it's going to find one of the elements on the page, and it's going to change whether or not it's visible. So I wanted to bring back one of the most, you guys don't see this anymore. It's really too bad. When I was a kid and I was browsing the web, you saw this all the time. One of the classic ways to draw attention to a certain part of a web page, make it blink. I'm serious. How many people have been to a page with blinking text recently? Where are you guys going online? Don't stop going to those web pages. I guess this one, right? There we go. Okay, I got you. You've been flash rolled. Yeah. So this is, again, you used to go to web pages all over the place and be blinking text and weird colors and stuff like that. But why is this text blinking? This text is blinking because there's a computer program that's running. And every second, that computer program does a little bit to change how the page looks and then goes back to sleep. All right? Okay. So, and let me go back briefly, quickly to this slide about web evolution. So when you go to most of the sites that you use today are not even these dynamic sites, even these second-generation web applications. A lot of the sites you use today are complete web applications. So what does that mean? When you go to the forum for this class, CS 125-forum, here's what happens. You get sent a huge blob of JavaScript that's a complete forum program that runs in your browser. When you click on one of the topics, the server does not send you a new page. What happens is JavaScript runs, JavaScript grabs some information from the server, and then JavaScript changes the layout of the page itself. So this is a completely different paradigm in web design that I probably have not explained enough about how the web works for you to appreciate, but that's okay. Many of you will go on and build, in the future, really sophisticated web applications using JavaScript. Why? Because what did you need to do to install the CS125 forum on your computer? Nothing, right? It's not an app, right? Back in the bad old days, you know, like when I was a kid, we had a music player app. I was showing somebody this the other day. It was called Winamp. How many people have heard of Winamp? Okay, like 10 of you. There's actually a new version of Winamp coming out after 10 years. I have no idea why, right? It's a completely unnecessary piece of software. Because when you guys want to hear music, you just go into your web browser, like go to Spotify or go to Google Music or whatever, and then, you know, go to town, no problem, right? Every time you do that, you're running a web application. Gmail's a web application. Google Docs is a web application. Our forum's a web application. A lot of, you know, again, when I was younger, you had a lot of programs installed on your computer. Now you can get away with having like 2 or 3, you know, a web browser, a terminal, maybe IntelliJ if you're developing Java code. 10 years from now, I suspect most of you will be doing your development in the browser as well. IntelliJ is like that last piece of code that still runs on your computer, but there are companies actually that are working on web-based IDEs, and I suspect they'll be usable soon. So at some point, essentially your computer is devolving into just a way to run a web browser. And in fact, if you think about Chrome OS, which some of you might have used, that's all it is. It's just a way to run a web browser. You don't install an application locally, you just use web-based applications to do things. Okay, I've talked enough about the future. Let's talk a little bit about web interfaces. Okay, so now you know roughly how the web works. When you go to, I don't know, whatever news site you go to, you make a request to the server sends you some HTML, some CSS, and some JavaScript, and your browser combines those pieces of information together to show you the page, and then JavaScript's also running that can do things like update parts of the page automatically or respond to interactions or whatever. So what's a web API? So an API, in computer science, it stands for an application programmer interface. The idea is that somebody wants to allow you to use some piece of software. They've created an interface. This is fun because it goes back to the interfaces we talked about previously. We talked about interfaces a lot in Java. We talked about Java's concept of an interface, right? It's this barrier across which there's communication. But I don't have to do that internally in Java. I can also do that externally across the web. And so a web interface is essentially an interface that's exposed over the internet. Okay, so how does this actually work in practice? So here's an example of an interface, and we've seen these already in Java, so I don't need to sort of dwell here, right? We've seen Java interfaces. An interface is a collection of functions that provide some related functionality. The interface creator documents that and then implements the interface somehow, and now you can use that interface to do useful things. You don't have to worry about how it's implemented or how it works, you just can use it. So a web API is an interface you access over the internet. So here's what makes this possible. I can send data to the server using a POST request, and I can retrieve data from the server using GET. So I can move information around. POST is kind of like making a function call, kind of. I'm sending some information to, you know, a particular endpoint, right? And GET is sort of, can also be thought of as kind of making a function call, right? The web server can run code in response. So this is a lot like an interface. When you call a function that makes part of a Java interface, it runs some code itself, right? And it can return a response. Here's where this gets interesting. So typically, when you guys browse the internet using your web browser, the documents that are sent to you by the server are web documents. They're HTML documents. They're designed for you to look at. But a web server can return anything it wants. It doesn't have to return HTML. It can return text. It can return XML. It can return JSON, right? So what we're doing is we're essentially building this entirely new paradigm on top of an existing system. So the web that got its start as a way to move hypertext documents around for people to look at and interact with, is now being repurposed as a way to enable programmatic communication between multiple devices. All right, so let's see how this works. There's other reasons to build interfaces this way that have to do with how the internet has evolved. I don't want to dwell on this, but there's reasons why this thing has been done. So let's map from our world of Java interfaces into our world of web interfaces. So let's say I had a function like this that was part of a Java interface that was supposed to allow me to access weather information. So if I'm going to call this function, what do I need to be able to do? If I'm going to call it over the internet. So I need to be able to take this weather location object of type weather location. I haven't told you anything about this object. That's fine. I need to be able to send information about that to the server. So I can do this in a couple of different ways, and you guys in lab this week are going to see multiple examples of how this is done. So one way is that I can stick it in the URL that I use as part of my get. And you see this. So I have to be able to take this location object and represent it as a string. And then I just stick it inside the URL. Now, a GET request to that URL will return the information I want. So that's one way to do it. We didn't talk about this, but this will be something we'll look at in lab this week. There's also a way to add query parameters to a GET request. You guys probably see this when you browse the web. So here's my URL, and then I have a question mark, and I have a series of key value pairs. So key is location, I have an equal sign, and then I have a string that describes that location. And I can have more of those separated by ampersands. I can also send a post request and just stick it in the body of the post request. So remember, when I send a post, I'm actually sending data to the server. So I have multiple ways to pass this argument to the server. Note that all of these require that I have to find a way to take my weather location object and convert it into a string. And this is one of the reasons we started talking about JSON in lab last week, and we'll continue talking about it, because JSON provides me with one way of doing this. Okay. So here's an example using post, right? I can send a JSON object in my post request with a key location, and then, again, whatever location information I'm trying to pass, represented as a string. How do I get, okay, so now I've talked about ways to get data to the server. So this is the equivalent of passing an argument to a function call. How do I get data back? So this get at location is supposed to return a weather info object. Again, I haven't told you anything about this weather info object, but you can imagine that it includes things like, is it raining, is it snowing, what's the temperature outside, maybe information about the forecast in the future, whatever, right? Information about the weather. So here's an example of how this would be done, right? Like I said before, a web site does not have to return HTML. It can also return text, it can return JSON, it can return XML, whatever. Here's an example of it returning some JSON. So this is an example drawn from an actual weather web interface. There's multiple of these that you can use as part of your app. Here's an example. So, and this sends you back this really quite detailed JSON object that has a lot of information. I'm just showing you a little bit of it. So this is this key called consolidated weather. This is sort of a summary. And then weather state name, thunder. So this is kind of like what's happening right now, summarized, thunder. Which direction is the wind coming from? When did you retrieve this information? This was last April. Minimum temp, maximum temp, here's an estimation of what the actual temp is right now. I think these are in centigrade. Wind speed, et cetera, et cetera. So now, as a string, I've been returned all this information about the weather. So I called this function by passing it a string that indicated the place that I wanted to find out weather for, and it returns back JSON indicating the weather. Because these interfaces are exposed over the web, I can use them to connect lots of different types of components together. So there's two things that are cool about this. One is that we're going to have you guys start thinking about this week as you continue working on your project. There are many, many, many different public web interfaces out there. A lot of them are free. Some of them force you to register, but then they're free. Some of them are free as long as you don't, make 1 million requests a day, which you're probably not going to. So these are great starting points for thinking about how to build your final project application. For example, last semester, one of the students in the class, actually who's a course developer now, Ben Nordic, built an app that uses data provided by the Cambridge bus service. So they have a web API. They provide data about where buses are and routes and stuff like that. And he used that information to build an app that allows him to figure out, when it's time to leave for the bus or whatever. Right? So by putting that information behind a web interface and allowing you to query it, the local transportation agency has made it possible for you to build apps like this. Ben claims that his app is better than all the other ones that they have up on their store. Given Ben, that's probably true. So if you guys use the bus, you should try his app. I think it's up on the Play Store. All right, let's talk about REST. We have 5 minutes. So as you guys start exploring these APIs in lab this week, you're gonna see this term come up called REST, or RESTful Web API, or REST Web API. I just wanna briefly talk about what this means. So essentially, REST is a design pattern for building web APIs. And the idea is that the things that the web API does are going to line up with the different types of HTTP requests. Or sometimes we refer to these as HTTP verbs. So for example, if I do a get to products, let's say this is an API for a clothing manufacturer, right? That allows me to get information about the things that they sell, or the things that they make. If I do a get on products, that should return a list of all the products that this particular manufacturer makes. If I do get on products 10, then what I'm doing is I'm asking for information about a specific product, right? So I can use the other HTTP verbs similarly, right? So get is gonna get me some information. Post is going to create something. So maybe with the proper permissions, I can actually use this web API to create new products. So I would post information about a product, and then it would get added to the catalog that I would retrieve using get. There's an HTTP delete command that does kind of what you would think, right? So delete would remove something, right? I also use the authorization codes. So remember from last time, whenever I make an HTTP request, I get a response back. That response includes a numeric code that is the server telling me what happened. 200 means okay. You guys don't see 200 because there's a web page in front of you and you're reading it. The 400 level are error codes. So 404 is very common. That means you asked for a page that doesn't exist. There are other ones like 405 means you don't have authorization for that particular page. So maybe you tried to delete an item from the catalog, but you're not an administrator or something like that, so you can't do that, right? So I reuse these HTTP response codes as part of my web interface. And they mean the same thing they would mean if I was using them on the web. And then typically in a REST API, the bodies of the responses are JSON. So they're serialized using the format that we showed you last week. So here's some a table with some examples. So again, if I do a get items, this is supposed to retrieve all items. Here's a Java-like function that might do the same thing, right? I can sort of overload. I can overload things. This is almost like an overloading here where I have 2 versions of items. I have one that gives me everything and one that just queries based on an ID. Here's this is sort of a search, right? So I'm giving it a parameter here as part of my GET request. It says, give me all the items that are Frisbees. Again, there's ways to map all of these into a function in Java that would do a similar thing. But again, these are not implemented in Java necessarily. All right. All right, I'm done with these. All right, let me pause here to take some questions. We're done talking about this. These were a couple of hopefully semi-fun lectures that we sort of stuck in between. Next lecture on Wednesday, we're gonna continue talking about, we have a couple of more Java programming concepts that we wanna work on this week, and then next week we're gonna do some cool stuff. But any questions about this? One of the reasons we're introducing this is we do expect many of you will build applications, will build apps for your final project that use a web interface. And there's some really cool ones out there. So last semester we actually did an MP using a image recognition interface that's provided by Microsoft. So Microsoft has a web API where you can upload a photo and it will tell you things about it. It will identify celebrities in the photo. It will tell you how many people are in it. It will give you some categories like this is a dog or this is a cat or whatever. This is incredibly cool, right? So you can think of a variety of different apps or interesting things you might want to build that could use that as a building block. You don't have to implement it. You could spend like 30 years trying to figure out how to do all the machine learning to get that right. Microsoft's already done it for you. They're exposing that functionality for you over the web. All right, any questions before we go on? Yeah. Yep. Yep. Yeah, so the question is, if I send a request to a web interface and it returns information in JSON, how do I work with that in Java? It's a great question. You guys will get some practice at this in this week's lab. So Java has libraries for parsing JSON. One of the reasons that JSON has become so popular is because pretty much every major programming language has good support for it. So I can send and receive JSON in Java, JavaScript, Python, Haskell, Ruby, whatever. And so this also, I just want to point this out, this allows your code written in Java, Python, JavaScript, C, C#, Ruby, Haskell, Scala, Go, whatever, to interact with code that's written on the server that runs in Java, JavaScript, Python, C#, C++, Go, Ruby, whatever, right? All of these languages have really good libraries for working with JSON, and you guys will have a chance to use one this week. It's a good question. Other questions about this? Oh, I should point something out. No weather applications this year. That's gonna be the one addition to MP6. I probably forgot to put this in the write-up, but we will not accept weather applications this year as a final project. Too many of them last year. They're boring. You guys can do something much more interesting than the weather application. It's not that much more difficult. Other questions? Okay, I'm really looking forward to seeing what you guys do for the final project. I think we're gonna have some really, really cool ones based on some of the conversations I've seen on the forum. Oh, I forgot to talk about this. Okay, that's too bad. No, I'm gonna talk about this, because this is useful. There's a few slides here at the end that are a review of sorting. I will just point out that this week's quiz is about sorting algorithms. I think I would rather use the next 5 minutes to talk about internet design principles than go back and review sorting stuff again, but there are slides in here that are copied from the last deck of slides we did on sorting. Just please be aware, this week's quiz is on sorting. It's all about sorting. If you are familiar with sorting algorithms, you will be prepared for this week's quiz. There's also a couple of review questions that are not about sorting, but are about things that we've covered recently. The programming questions this week are not about sorting. For reasons that will become obvious once you take the quiz. But there's a question on trees, there's a question on using Java's built-in list types. Okay. One of the things, so I want to just step back for a minute and talk about one of the things that's really cool about the internet. So one of the things I said on Friday is that, you know, we should all be really thankful as computer scientists that the internet exists in its present form, because it's very, very, very possible that we could have ended up with a completely broken, fragmented, awful version of this system. If you look at Bluetooth, if you look at what's happening in the home automation space right now, this is what the internet could have become. You could have had the Microsoft internet, the Google internet, the Apple internet, the Facebook internet, and when you purchase internet service, you have to check boxes like which websites do you want to visit, you know. It could essentially have become like cable. That's not what we got. And what we got is this incredible thing that's enabled an enormous amount of innovation, but at the same time, there are efforts underway to sort of chip away at some of the core features of the internet that have made it so powerful in enabling innovation. One of the core internet design principles, key to how the whole thing operates, is this principle called the end-to-end principle. So what the end-to-end principle says is that the network itself should be simple as possible. If you look at what the IP protocol does, it's a very, very, very small set of features. What the end-to-end principle does is it says, push intelligence to the endpoints. If you need some other feature on the internet, implement it at the client and at the server. Implement it on the two devices that are talking to each other. Don't try to stick it into the middle of the network. Keep the network itself as simple as possible. Push intelligence and new features and new capabilities out to the edge. All right? One of the really interesting things about the internet, and I suspect many of you did not know this, the core internet does not guarantee that data is transmitted reliably from point to point. If you send a packet from this room destined to Timbuktu, it's possible that somewhere in the internet, as that packet is being moved from machine to machine, it's going to get dropped. It's possible it's going to arrive at a machine that's too overloaded to accept it, and it's going to get dropped. And you know what the internet's going to do about that? Nothing. The core internet does not guarantee that your data moves reliably from point to point. So how does your data, I mean, when you go to a website, you expect the whole thing to be there. You don't expect to load the website and there's like a big hole missing because some packet didn't arrive. But reliable delivery is not guaranteed by the internet protocol. Instead, what we've done is we've moved it out to a separate library. Part of the reason for this is not every application needs it. Let me give you an example of an application that doesn't need it. So if you're streaming video, let's say that you're streaming video from one machine to another, and there's one frame of that video that, again, gets misrouted or arrives at a machine that's too overloaded to accept it or whatever, and gets dropped. By the time you retransmit that frame, it's not needed anymore. Like the video is 5 seconds into the future, and there's no need for that data to arrive. So not every application needs reliable delivery. Therefore, the internet protocol doesn't provide it, which is really interesting. So again, we move this to the endpoints. So when you are trying to download something reliably over the internet, there's code that runs on your computer, and there's code that runs on the server that you're talking to, and there's an additional protocol called TCP, which is mainly what we're using today, although we're starting to explore alternatives, that's responsible for making sure that all the data arrives. So when you download a website, if there's one little piece of information that doesn't get there, your computer will go to the server and say, hey, I never got a copy of this, and the server will say, oh, okay, sorry, I'll send it again. This is done on top of IP. This principle has essentially allowed the internet to evolve, and it's allowed us to build lots and lots of things on top of it. And the core network stays simple. The network doesn't choose winners and losers. That's the other thing. So the core internet doesn't discriminate between Facebook and whatever new social networking site will maybe someday rise up and challenge Facebook for supremacy. The internet doesn't do that. It was never designed to do that. It shouldn't do that. We had this debate a year ago. There's been some changes in this space, but I just want to alert you guys to this because you guys are young, new technologists, and you will have an impact on this issue. What net neutrality is, put simply, from a computer scientist, is it's a legal enshrinement of the end-to-end principle. Net neutrality is nothing more than an attempt to protect, legally, the same features of the internet that made it so successful. Namely, again, the internet doesn't pick winners and losers. Facebook shouldn't be able to pay more to an internet service provider to get better service. Google shouldn't be able to either. We wouldn't have the internet or the world of technology today had this been possible. So again, you guys will cast votes about this. You guys will lobby about this. Some of you will be in positions of authority and power to do the right thing. Please do the right thing because, like I said, the internet is this incredible miracle, but it's also fragile. And things like this are attempts to chip away at some of the things that has made it so successful. Good luck on this week's quiz. I will see you all on Wednesday. One note is that I do not have office hours this morning. I have a crisis at home I need to attend to. I may be back in the afternoon. Otherwise, I'll see you guys on Wednesday. Enjoy lab. Welcome back.